Everything is going perfectly. Your user base is scaling, traffic is through the roof, and then you check your cloud bill. A line item you barely planned for has suddenly overwhelmed your entire infrastructure budget. That line item is data movement. Cloud providers aggressively market how cheap it is to store your data, but storage is only half the equation. Moving that data around is where budgets break. It comes down to ingress versus egress. Ingress, bringing data into the cloud ecosystem, is almost always free. The providers want your data. But egress, when that data leaves their network to reach an end user or another service, is heavily metered and billed per gigabyte. This chart highlights the problem. Your storage volume plots a slow, highly predictable upward slope, but your egress traffic is driven by user behavior. When your application scales, those outbound data requests spike exponentially. Direct and serious, guaranteeing financial penalties. As seen by this shaded deficit zone, your total cost depends on how often data exits the network. For finance teams, egress fees introduce volatility that makes forecasting difficult. Because these charges fluctuate based on user demand, mapping an accurate total cost of ownership becomes a moving target. For architects, the dilemma is structural. Standard microservice architectures and global deployments rely on constant communication between servers. In the public cloud, the default network routing actively penalizes this chatter. You are left with a choice: accept the easy default configurations and pay the hyperscaler toll, or invest engineering hours upfront to defend your margins. Data transfer fees are a structural vulnerability in your system design. Addressing them requires architectural engineering, not just financial oversight. Look at this matrix of the big three providers. Standard internet egress costs hover between 8 and 12 cents per gigabyte. Expanding this reveals a hidden premium. Moving data between regions costs another 9 to 12 cents per gigabyte on their internal backbone. Relying entirely on these default pipelines exposes your business. If a marketing campaign goes viral, those pennies multiply into terabytes, turning a successful weekend into a massive billing event. Achieving global reach through hyperscaler default settings is a financial trap. To survive, you need an intervention layer. For internet-bound traffic, your primary shield is a content delivery network, or CDN. This flowchart maps out the bypass. Instead of users pulling large media directly from your main cloud origin server, they pull from localized edge cache nodes hosted by the CDN. The impact is immediate. A properly configured CDN can intercept and serve up to 80% of your traffic, dropping your origin egress volumes to a fraction of their previous levels. But this introduces engineering complexity. Edge caching requires strict cache invalidation rules. Your team has to actively manage these edge nodes to ensure users aren't downloading outdated versions of your application. Utilizing a CDN successfully shifts the burden. You stop paying for raw metered bandwidth and start paying in engineering oversight and configuration time. Your external traffic is only half the battle. Inside your architecture, chatty microservices crossing between different availability zones generate silent, compounding fees every time they exchange a packet. By default, your servers might route traffic over the public internet to reach other cloud services. But by configuring VPC endpoints and private links, the route snaps into a direct enclosed tube, keeping the data entirely within the provider's private network. This single routing adjustment usually drops internal transfer fees down to roughly 1 penny per gigabyte. Next, you have to optimize the payload itself, moving away from bulky text-based JSON formats to binary formats like protobuf, and compressing the data with Brotli or gzip drastically reduces the size of every request. Compressing these pipelines does require more CPU cycles, which increases your compute costs slightly, but CPU time is significantly cheaper than paying raw egress fees for uncompressed data. By combining private routing links with heavily compressed payloads, you shrink your digital footprint before it ever reaches a metered toll. If your workloads are inherently data-heavy, like video streaming or massive backups, optimization might not be enough. The ultimate strategic pivot is repatriation, migrating to bare metal servers or zero egress cloud providers. Think of cloud billing like this toll booth. The major providers operate a complex, metered lane where prices fluctuate based on volume and region. Bare metal providers like Latitude.ss or storage specialists like Blackblaze operate the express lane, offering flat-fee, predictable billing models with massive free egress quotas. The trade-off here is severe. Leaving the hyperscaler walled garden means sacrificing their fully managed native tooling ecosystems. Your team will have to navigate a much more complex hybrid cloud operational model. However, for organizations where budget predictability is the highest priority, accepting that operational complexity is a mathematically justified decision. Before you choose a path, you need visibility. Deploying cost allocation tags across your cloud resources is the only way to build an early warning system. You cannot fix a leaky architecture if you don't know which service is bleeding data. This decision tree outlines the action plan. If you are a fast-growing startup with media-heavy workloads, prioritize CDNs and payload compression immediately. You need to insulate yourself from sudden viral scaling. If you run an enterprise data team, focus heavily on VPC endpoints and co-locating your data processing. Keeping your compute in a same region as your storage avoids the punishing cross-region taxes. And if your business model demands absolute financial predictability, begin migrating high-volume backups and streaming workloads to zero egress alternatives. Sustainable cloud growth requires designing an intentional path for data to leave your network without eroding your margins.